Hello physics students. So in this video we're going to be talking about electrostatic potential energy. So remember, this is the third of our 4 foundational ideas that we're going to be learning in this unit. One is that there's a force between charges. Opposites attract, plus minus. Like charges repel, plus plus, repel, minus minus, repel. That was the first idea. The second idea was electric field. We had to refine our description of how the force actually was created. Charge 1, maybe as a proton, creates an electric field pointing away from it, a disturbance in space over here. Now when you put an electron here, instead of saying plus minus attract, we say the electron feels a force in the opposite direction of the electric field, still attracting. But that extra step was to be more accurate in how the universe really works. So there we had force, electric field, and today potential energy. Okay, so the third idea coming today. So potential energy, think about, we have gravitational potential energy. So we're going to kind of be piggybacking on that idea because you already have a concept of what potential energy is. But before I jump into the specifics of the electrical potential energy, I just want to point out that the forces, in order for there to be potential energy, the forces have to be what we call conservative. I'm going to explain what that means, but I'll pause the video to give you an opportunity to jot this first portion of the board down. Okay, so a conservative force. Let's suppose I'm moving an object from one point to another, initial to final. One definition of a conservative force is that if you move the object along different paths, like for example, directly along a straight line, or if you move it past the point and return, or you go along some kind of curved path, but in all instances you begin and end at the same points, the work done by that force is the same. In other words, it only depends on where you start your journey and where you end your journey. That's one definition of a conservative force. Another definition of a conservative force is that if you move an object from here to there, I should have called those A and B, I suppose, because we're going to reverse the path in the second. So let's say from A to B, and then you calculate or you determine how much work that took, or how much work was done by the conservative force. Then you move it back the opposite way. Then what's true of the work done in the second motion, it's exactly equal to but opposite sign of the work done in the first case. So that's the same case with gravity. If I lift something like this and gravity does negative 10 joules of work, why is it negative? Because the force of gravity or from the earth is this way, but I'm moving that way. FD cos 180 degrees. FD cos theta is the formula for work. So 180 degrees in the cosine function gives you a -1 number. So the negative work done by gravity to lift this, 10 joules, -10. If I let it go down, then the work done by gravity would be +10. So this gravity satisfies this and this definition. Friction, on the other hand, is not a conservative force. If I drag something along a tabletop and the work done by the force, if I move this way, friction is that way, so -10 joules to move it this way. Then when I drag the object back along the table, friction is now this way, and the motion is now this way. The angle is 180 degrees. So -10 joules and -10 joules again. Not -10, +10. So friction is not a conservative force, which is why we can't have potential energy of friction. Okay? You can only have potential energy of conservative forces, and Fe satisfies that. Okay? So that's, you do 10 joules, it does 10 joules of work, -10 if it goes the other. And that's true of the electrostatic force as well. So then Knowing that, we can now say that there's potential energy. So I'll pause the video now so you could copy down this next bunch of notes here. So I'll give you a minute for that. Okay, so let's suppose we've got two charges. Here's the formula for the electrical potential energy. This is the Coulomb's constant, 8.9910 times 10 to the 9th. You could use 9 times 10 to the 9th. These are the two charges. Oh, mistake. Sorry about that. Make sure you take away that r squared. It happens because you're so used to Coulomb's law, and if you're not thinking carefully, paying attention, you might insert that squared too. But no squared in the denominator, just to the 1 power, okay? Now, it's important to understand exactly what this means. So for a good portion of this video, we're going to concentrate on the concepts behind, because there's a lot of subtlety and you have to understand all those concepts to get all the questions right on the possibly on the AP. So what is this? When you plug this in, you're going to get some number of joules, 10 joules or -8 joules, some value of potential energy. This is not the work to move Q2 along this path right here. You might say, well, that's in the formula. And when I said UG gravitational is mgh, well, the h in the formula was just here, and that's how high you lifted the object, right? So h is the path that the object moved in, not here. The path of the potential energy is not here. What it is, and this is the first big concept, is the electrical energy is negative the work done by the electrostatic force when the object begins at infinity and moves to this point, which is r away from Q1. So this is the path over which we're calculating the potential energy change from that formula, okay? So that's what I wrote out here, not the work to bring along r. UE is the negative work done by FE to bring Q2 from r initial infinity to r final right there. Now, why the minus sign? Well, let's just think about gravity. When I lift this, first of all, it's not the work done by me, because when I lift something, I could lift this mass here slowly and put in maybe 2 joules of work. Or if I move it from this point to this point, again, I could go as hard as I can and put more force into it. And instead of 2 joules of work, maybe I put in 20 joules of work. So the amount of work that I put in from one point to another depends on my effort. So what we want to do is not the force that you put in, but the force done by the conservative force. That's what's always the same between 2 points. And with gravity, if I'm lifting and I start here and end here, the work done by gravity will be the same every time, and it'll be negative if I'm lifting the object. Why negative? Again, as I said, force of gravity goes this way. The motion is that way, FD cos theta with theta 180. Negative 2 joules of work to lift this marker up to here. But the potential energy change is positive when I lift and negative when I fall. So when the work done by gravity is negative, I want U to be positive. I got to put an extra minus sign in there. And now I have how much potential energy to go from here? -2 joules, which is positive 2 joules. When I let this go down, the work done by gravity will now be a positive value. Force of gravity, motion, FD cos theta, theta 0 degrees gives me that the force of gravity did positive work. But we know potential energy should be getting smaller. The change should be negative when something falls. So we say negative of the positive work done by gravity is the negative potential energy when something drops. So that's why you need a minus sign always with all potential energy calculations. So when you go against the force, you're actually increasing the potential. And when you go with the force, you're decreasing potential energy. Okay? So that's it. And it's the same thing with charges. If I have plus, actually, you know what? I'll hold off on that. We'll talk more about that the concepts, how this relates in a minute. But what I want to do first, before we move on to building more on the concepts, I want to prove this, because that's actually in the curriculum, that you prove that that's the potential energy. So make a little room here. Okay. So the proof. Okay. So as we said, the potential energy, electrical, will be minus the work done by Fe. In other words, I'll put a minus sign here, but I can't use the formula work equals Fd cos theta because the force varies. So what I have to do is convert Fd cos theta into an integral. First of all, the cos theta, the force and the motion, I'm going to have them in the same direction. So let's just, or you know what, let's do the dot product. And then we don't need the cos theta. So minus the integral from initial to final F E dot dr, because we're moving in the radial direction, not along the x-axis, but along the radial direction. So there's basically this, but for f dx, but we're going to use dr instead. Okay, so we converted this to a summation of force times distance over little tiny distances. We're going to add up force times distance plus force times distance plus force times distance from one to another, location to another. That's integration. Okay, so let's continue on. So, oops, I forgot the minus sign. From infinity to R final, the expression for the force is this, and the force and dr are lined up in the same direction, so I will just get rid of the dot product, and then minus you know, I'm running out of room here, so let's try going down here a little bit more, hopefully. I'm just going to rewrite this as a power, just to help us with the integration. This is just a simple power rule. So what I'm going to do is I'm going to now add 1 to the exponent. So instead of to the minus 2, I make to the minus 1. Okay. And then I'm going to divide by that new exponent. You know, it's kind of crunched, so let me spread it out a little bit more. And then for my limits of infinity to R final. Now notice the minus signs go away, and so now I just need to plug in my limits. So K, Q1, Q2, R to the minus 1 is 1 over R, so I plug in R final first, and then I plug in 1 over infinity second subtracted. Now this is 1 over a large number, 1 over infinity. This term is 0, and that gives me my final expression of K, Q1, Q2 over R. And I'll just drop the R final, but that is the expression. So there's the proof. I'll pause the video to give you a chance to catch up. Okay, so integrate FDR and basically plug in your limits. Don't forget the minus sign because this should end up positive at the end. Okay? Now, I want to talk a little bit more about the concepts and how this potential energy function specifically works. So let's suppose if the charges are the same sign. So if you plug in positive here and positive here, or negative here, you get a positive answer. And by the way, in this formula, you do have to plug in minus signs for it to work. So with force and electric field, I told you, because they were vectors, use the minus sign just to determine which way the arrows point with those. This is a scalar. Potential energy doesn't have a direction. Energy in general doesn't have a direction. Whether you're going north or south with your car, it takes the same amount of gasoline to accelerate you up to speed. Okay? The direction doesn't matter. But that means that now you have to plug in any minus signs into the formula so that the scalar value will factor in the negative charge by introducing a minus sign. But if the charges are the same, then the potential energy is positive. And the plot of that function then looks like this. Okay? And what that means is now, so let's suppose we got proton, proton. If I move this proton to a smaller radius, it wants to go this way, right? So what I have to do is I have to kind of like lift it. Just like when I lift the weight, I go against gravity. Well, this, I'm going against the force. I'm lifting it this way. Right, I cram that proton in. And now I've gone to a higher potential energy because I'm lifting it. Is that what we see in the formula if we have R initial here, and then we cram the charge in to a smaller radius, so R final, right? I'm cramming it in. What you see is that the initial potential energy is right here. I'll put UI for initial. And the final potential energy is right here. And so we see the correct concept that the potential energy increases. So as R goes down, U electrical goes up. The concept is consistent with our understanding of potential energy. And then if you go the other way, as R increases, so you move from here to here, you see you go to a lower potential energy. So when I have proton, proton, or electron, electron, and I let it go, it's like falling. So potential energy is going down and kinetic energy is going up. And that's what we see when the radius gets bigger, the potential energy got smaller. So the formula is so far consistent with our understanding of potential energy. What about if the charges are opposites? Well, then you plug in a positive number here and a negative here, you're going to get a negative answer for potential energy. And so it's this graph, but underneath. Always negative. But the same thing, as R goes to infinity, the function goes to 0. So as R goes to infinity, it gets closer to 0. Same here, as R goes to infinity, it gets closer to 0, but starting from the negative direction. And as R gets smaller, U goes positive high or negative high. Well, I guess that's like decreasing. All right, so there is the shape of the graph. Once again, so now we've got proton and electron, opposite charge. How do I lift this charge? It wants to fall this way. To lift it to higher potential energy, I've got to lift it up like this, right, and push it out here. let it go wants to fall, right? So increasing R is increasing the potential energy. Do we see that from that graph? Let's take a look. Let's suppose R initial is right here. So the initial potential energy is right here. And then I lift this charge. In other words, I'm lifting that electron away from the proton to a higher radius, right? So there, that's R final. Did I increase the potential energy? Well, here's the potential energy final. So to give you some numbers, maybe this is like -10 and this is -2. That's an increase of +8. So yes, even when the charges are opposite, it works that as R increases, you're lifting the electron away from the proton, the potential energy also increases, as we could see. And as R, decreases, now it's falling, right? So we let the electron fall, and it's losing potential and gaining kinetic, right? It's going to slam into the proton. So we see the potential energy is getting less, meaning the kinetic energy is going to go up as that falls. So those are the concepts behind this. Lots of concepts. It's the work coming from infinity done by Fe minus sign, right? So that's the first big concept. And the other is that you have to plug in the charges and then the idea of positive, negative, you're lifting, falling. Positive, positive, you're lifting and falling, okay? And it's shown by the graphs. Now what I'm going to do is show you how this formula works with a couple examples. So, if you haven't already done so, I'll pause the video, give you a chance to catch up with the notes. Okay, so let's take a look at example 1. Okay, question mark. So we've got a proton and electron, and here's the proton, here's the electron. We let the electron go, and we could let them both go because the proton's so massive. It's almost 2,000 times more massive than the electron. So even though it's attracted to the electron, it's pretty much going to stay put. We could ignore its motion. So this electron is going to accelerate in and come in, and we're going to use energy to figure out the speed of that electron at that final point. By the way, you can't use Newton's laws conveniently because the force varies and the acceleration varies. So you can't find the force and the acceleration and then V equals V initial plus AT here because, or some formula because the acceleration changes throughout the motion. So we can only pretty much use energy. So here's the proton, and the electron is like right here initially, and then it's right here final. So this is the initial and the final accelerated in. So in the beginning, the way we solve this is we follow the same process we used in mechanics when solving energy conservation problems. We ask ourselves, what are all the kinds of energy that the electron here has in the beginning? It's at rest, so there's no kinetic energy. This is in space. Well, there is gravitational energy, but it's negligible compared to the electrical energy. So all we have is U electrical, initial, and you could write K equals 0 if you want, but you don't have to. Over here, when it's over here, at this location, we still have electrical potential energy, because electrical potential energy is 0 only for R at infinity. So we're not at infinity, so we still have electrical energy. But now we have kinetic energy because we lost potential. So that's going to be picked up as kinetic. And so now what we do is we say energy before equals energy after. So we could say U electrical initial equals U electrical final plus kinetic energy. Okay? Now, this is K. Now, for the electron and proton, I'm going to use plus E for the proton. That's 1.6 times 10 to the minus 19th. And minus E, negative 1.6 times 10 to the minus 19th. So there's the initial potential energy. The final, oops. So I'm actually not going to plug in the numbers here because, I think you can see that it's done, and I don't want to make the video too long. It's already going to be on the longer side. But 9 times 10 to the 9th goes here and here. 1.6 10 to the minus 19 goes in all the E's because the proton and electron have the same charge but opposite sign. R initial was 1.5 times 10 to the minus 9th. R final, 1.0 times 10 to the minus 10th. The mass of an electron, that is on a reference table that you actually get for the AP exam, or you could look it up in the textbook or online. It's 9.11 times 10 to the minus 31 kilograms. And so the only unknown is V. And it's just a lot of crunching on your calculator, but that's all, okay, to get that solving for V. I'll pause the video to give you an opportunity to jot this down. Okay, so one more example that I am not going to do in great detail. I'll just mention the strategy for solving it because it's not that common, and to actually punch the numbers again would be kind of tedious, so I won't go into all the detail. So. Okay, so determine the work necessary to assemble the following charge configuration. I'm going to take 3 charges and maybe bring them in and glue them to a tabletop. Q1 here, Q2 here, and Q3 here. Okay, so that's the arrangement, but to show you the thinking behind this and what we mean by the work necessary to assemble the following charge distribution. I'm going to erase all these charges again. You could leave them if you already jot them down. Don't worry about it. But, okay, let me just make little dots where these were, right there, there, and there. So, but the charges, pretend they're not there right now. So I have 3 charges, Q1, Q2, Q3, and I want to make this triangle out of the charges. So the first charge, I bring it from infinity, from far away, and it's free to bring that charge in. In other words, I don't have to do any work, because I could start with this in deep outer space and give it a little, and wait like 1,000,000 years, and it's going to so I did hardly any work. It'll come here all by itself, okay? And whatever work I put in to get it moving, I'll get it back when I bring it to rest. So the work to bringing that in is 0. But now, let's assume all these charges are positive. I want to bring the second charge in. So now I'm starting maybe from out here out at infinity. And let's suppose positive, positive. Now, it's repelling from that charge. The whole way in, I got to push it in, right? Because it wants to go this way. So I'm doing work to bring that in, and then put a little dab of glue, and I glue it in place there. I got that there. But the amount of work will be the electrical potential energy, because that's what potential energy is. It's the work from infinity in. So this is U electrical 1. And so, well, I'm kind of getting ahead of myself. So that's the work between charges 1 and 2. Okay? And then, now when I bring, the third charge in, let's suppose it's positive also, and these are positive. Now, what I'm doing is I'm trying to push it in, but it's repelled from both of those. So I'm pushing that in, right, as hard as I can, and there's an amount of work that I do before I can get it to the table and glue it to that spot, okay? So that takes a certain amount of work that's going to be equivalent to the electrical potential energy between these two charges, because they're repelling. These two are repelling. And let me add a little subscript here. 1, 2, 1, 3. Okay? And there's a certain amount of work from the repulsion of these two, which is just the electrical energy between 2 and 3. So if I want to find the net work to assemble, it's all of this potential energy added together. So let me erase this and say that it is U electrical between 1 and 2 plus U electrical between 2 and 3 plus U electrical between, 1 and 3. And 2 and 3. Okay? So, like I said, I am not going to plug in all the details, but basically you would just do KQ1, Q2 over R, KQ1, Q3 over R, and KQ2 and Q3 over R. So you do the sum of U electrical for all pairs. And that's the work to assemble. Okay? One pair, one pair, one pair, you use the formula 3 times. So for 3 charges, you have 3 terms. I'll pause the video to allow you to jot that down. Okay. Now, one final point, I want to just point out that calculating the work to assemble charges can get pretty tedious pretty quickly. Let's suppose you had 4 charges. So you add up the potential energy for all pairs. Well, here's 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs, 6 pairs. So you would have 6 terms. You'd be using the potential energy formula 6 times. Very tedious. Imagine 5 charges, right? So on the AP, you're not likely to encounter charge configurations beyond 3. Because, remember, free response questions are 15 minutes. Multiple choice questions are 1 1/3 minutes, I believe. So if they make a problem with 5 terms, well, you're going to take you 20 minutes on just that one part, one calculation. So it won't enter, not likely on the AP. Okay, so that's electrical potential energy. 3 ideas so far. There are a total of 4. Force, electric field, potential energy. It's like gravitational potential energy. When you lift something against the force, you have positive potential energy. When you go with the force, negative. So when you have plus plus, you lift against the force, that's positive potential energy change. Or when you have plus minus, you lift against the force to have positive potential energy change, and negative the opposite direction. So that's the concept. Another concept is that it's the work done, negative work done by the force from infinity to a point. So it's always from infinity in. So that's another concept. And then the concepts of the calculation using the formula, which isn't on the board right now, the K, Q1, Q2 over R to the 1 power, okay? And understanding how you have to plug in positives and negatives in that formula. And also the proof, how you integrate that formula, KQ1, Q2 over R squared, that's the force, dr. You integrate that with a minus sign from infinity into R final. So a lot of stuff for today. Look back, review your notes, make sure you get this idea rooted in your head. Remember, those 4 ideas are used for a good half the course. So if you kind of don't get this and you move on, you're going to have shaky foundation for months of physics, electricity, and magnetism. So make sure you really understand the concepts before you go on to today's homework. So that's it for today. I hope you enjoyed electrical potential energy, and I'll see you in the next physics video. Okay.